particles push against each other, and in this case they actually reach a decent kind of equilibrium at some point, and they steady down a bit there. Now these values are absolute. The other option that you have is to use relative to particle size, which we can activate here. Relative to particle size uses the size of each particle as a multiplier for the range values. So we have a core value, and this defines the range up to which the force is at full effect, and it's expressed, as you can see, as a percentage of the actual particle radius. And the actual particle radius is set up in a shape operator, and whatever the size is of the particle shape, that's the actual radius, which will be picked up on in the keep apart operator. You can see at the moment I'm using a 100% radius size to define the core radius of the actual force, and you can see that I'm using a 100% value to actually define the fall off range for the actual force. And you can see you have a percentage variation that you can apply per particle. So this is obviously much more useful when you have particles with varying sizes, and you want particles with bigger sizes to have bigger ranges, and you want particles with very tiny sizes to have much smaller ranges, and that those ranges are then based on the actual size of the particle rather than on absolute units in max. The next values that we can look at are the scope values, which you can see here. And you can see at the moment we're using the current event scope, and basically what we mean by scope is which particles does this particular operator have an effect on. Now it's interesting in that it can actually affect particles from other flows. So if you have more than one source in your scene, you can actually say that we want to use the current event, which we're using here, so it'll actually only affect particles in this current event. Or we can say we want it to affect particles in these current particle systems, which you can actually pick here. So you can actually pick up the different particle systems here. You can see this particular scene has speed operator, particle flow, speed by surface, speed by icon, and keep apart. So you can choose any one of these or a combination of these by holding down control to actually choose which particular particle flows these particles will actually affect. So you can choose that there. The other option is to actually pick your effect by using selected events. So again, you can actually choose which events are affected, and you can see the events from the other particle flows are actually listed here. So we've got event 5 in this particular particle flow, and you can see you've got event 2 from one of the other particle flows and event 3. So you can see that in this particular case it would have been a good idea to actually name those events, to give them names which were representational of the actual flow that they're in. But in this case I haven't actually done that, so they've just got generic names like event 1, 2, 3, 4, 5, whatever. So using this particular scope value here, you can actually choose what particles these particles will actually keep apart from. So it's very useful in that respect, and it can actually allow you to have your particles in one event affect particles, not in just one event, but actually affect particles in other particle flows, and also affect particles in other particle events, or you can just limit it to the current event that you're working in, which you can see we're using here. And the last option that we have is uniqueness. In this case, if there are any sort of random values that you have here, for instance, we've got variation, you can change the variation application by actually generating a new random seed. Now, I should explain with this particular example, it's quite unusual. I've used it to demonstrate how this particular operator works, but it could be a little bit deceptive maybe. What I've actually done here is I've used a cylinder as a collision object. And you can actually see, we've got the cylinder here. So if I change our orientation a little bit, actually I'll just put it back here. If I change our orientation a little bit, you can see that the cylinder is very, very, very thin. And this basically keeps our particles in a plane. And that means then that when they push against each other, they keep in that plane. And therefore they basically eventually arrive at this sort of relaxed state, where they're all at equidistant distance from each other. And every now and again one of the particles pops orientation as it tries to change its position. It's trying to keep apart throughout the duration of the entire animation. Now something I was going to show you, which is this gravity field here. So if I turn on force, you can see that these particles are orienting themselves towards this force here. And so you can see that the keep apart operator doesn't have a completely rigid effect on the actual orientation of our particles. And you can see they relax into a sort of steady state, and then our force travels through and the particles are pulled towards it. But you can see that once the force has actually passed through our little petri dish, you could say. These are